Welcome to Sustainability Speaker Series, and thank you for coming out today. Please help yourself to hot chocolate, tea, or water at the back. Today we are gathered on Treaty 6 territory and homeland of Métis. On behalf of the Saskatoon Public Library, we pay respect to the Indigenous ancestors of this place. As an organization that played an important role in the settlement of Saskatoon and as a key memory institution, we acknowledge our responsibility to respond in meaningful ways to the calls to action. The program tonight can only happen because of the partnership the library has with the Saskatchewan Environmental Society, who work hard to find knowledgeable speakers month after month. I'd like to invite Carol from the Saskatchewan Environmental Society to come up and introduce our tonight's presenter.
So my name's Carol. Good evening. And I'm a volunteer with the Saskatchewan Environmental Society. The Saskatchewan Environmental Society has worked on environmental issues in the province for over 50 years. The Environmental Society works on a wide range of issues, including climate change, renewable energy generation, opposition to nuclear power development, protection of Saskatchewan's water resources, and preservation of important wild spaces and habitat. We invite you to become a member of the Environmental Society. The Saskatchewan Environmental Society's newsletter, The Environmental Resource, has information on ways the Society is working towards a world in which all needs are met in a sustainable ways. You can sign up to receive the newsletter at the website environmentalsociety.ca. If you would like to receive an email reminder of events in the Sustainability Speaker Series, you can add your name to the sign-up sheet on the table near the entrance to this room. Also on the table near the entrance to the room, you can find a handout from Clean Green Saskatchewan, and also the website address, which is, it's on the handout, but if you just want the website address, it's written down on the sheet of paper there. Our speaker this evening is Gordon Edwards, who's joining us using Zoom technology. Gordon is the president and co-founder of the Canadian Coalition for Nuclear Responsibility. This is a not-for-profit organization that was federally incorporated in 1978. The organization focuses on issues related to nuclear energy, including non-nuclear alternatives. Gordon is a graduate of the University of Toronto with a gold medal in mathematics and physics. He has 2 master's degrees from the University of Chicago and a PhD in mathematics from Queen's University. He has authored articles and reports on radiation standards, radioactive waste, uranium mining, and the economics and health risks of nuclear power. Some of you may remember a debate in Saskatoon between Gordon Edwards and a supporter of the nuclear reactors when Saskatchewan was considering building a large nuclear reactor. More recently, in 2021, Gordon made a presentation on uranium in the Sustainability Speaker Series, and a recording of this presentation is available on the internet. And if you want to find it, you can go to the SES website. There'll be links. Tonight, Gordon Edwards will discuss we'll discuss smaller nuclear reactors, including small modular nuclear reactors, often abbreviated SMR. The title of his presentation is SMR, Spending Money Recklessly in Saskatchewan and in Canada.
Thank you very much, Carol. Welcome, everybody. Thank you very much for coming out on this snowy evening. I gather you got quite a snowfall there. Just going to launch into my slideshow, spending money recklessly. Obviously, this indicates my point of view. I do believe that it's a waste of our scarce resources at the moment to be spending money on speculative, unproven, and very slow and costly new nuclear reactors. Small modular nuclear reactors, spending money recklessly. So the introduction here is to understand the status of the nuclear industry. This is a very important background for understanding where we are right now. It's important to realize that the nuclear industry has been stagnant worldwide for the last 25 years, for a quarter of a century. 25 years ago, there were 438 reactors. Today, there are 442 reactors. That's just 4 more reactors in that entire quarter of a century. And the actual share of global electricity provided by nuclear has gone down in that period from 17% to less than 10% today. And of course, electricity is only one slice of the energy pie. So that 17% 25 years ago represented only 3.3% of global energy. And today it's less than 2% of global energy. So when people talk about nuclear energy as a savior of the climate crisis, one has to be very skeptical of the potential of nuclear to fill that enormous gap. Now, here is another graph from the same organization, which goes up to 2022. The previous graph only went up to 2019. And it shows the same kind of leveling off for the last 25 years. The colors represent different regions. The top color, the green, light green, pale green, is West and Central Europe. The blue is North America. Russia and Eastern Europe is the orange. And Asia is the gray region. Now, it looks like the gray region has increased considerably in the last 10 years, but in fact, it's not much bigger now than it was back in 2008. If you make a comparison there, you see it's only a little bit higher. So even in Asia, the growth has not been as spectacular as one might think. So the nuclear industry has realized for a long time that this stagnation is not good for the future for them. And so they launched a nuclear renaissance, what they called a nuclear renaissance, around 2001. And at that time, they were anticipating that thousands of new reactors would be built around the world, certainly hundreds and maybe thousands. Large reactors, we're talking here about quite large reactors, not the small ones that they're ballyhooing at the present time. But this did not work well. In fact, there were only a handful of orders. And Westinghouse, in fact, bankrupted itself trying to build 4 large nuclear reactors down in Georgia and South Carolina, the AP1000 model. They had to declare bankruptcy. They've come out of bankruptcy since then, but they suffered $9 billion in losses from new nuclear projects. And in fact, the South Carolina abandoned 2 of those 4 reactors, even though they were largely built. So they wrote off billions of dollars in debt. And the 2 in Georgia are now operating, but at a great cost. The US federal government had given $8.3 billion in loan guarantees on the financing of the 4 reactors. Now, this is because private capital does not want to invest in nuclear. In fact, Wall Street advises people, their own investors, not to invest in nuclear unless there is a federal government guarantee of the loan, which means that you're really investing risk capital with no risk. Now, another example that was quite telling was the collapse of the French giant Areva. One of the stars of the nuclear renaissance was a reactor in Finland, the Olkiluoto 3 reactor, 1,400 megawatts, quite a large reactor. It began in 2005, and the plan was to have it operational in 3 years at a cost of 3 billion euros. But in fact, it didn't start up until 19 years later at a cost of 11 billion euros, almost 12 billion. So it took 6 times longer to build than promised and cost 4 times more dollars than was estimated originally. And this is the problem with nuclear generally. It has suffered traditionally from large cost overruns and large delays in construction time. So this means that it's not a very good option for fighting a crisis. If you have a climate crisis and you have to act quickly, nuclear is not the way to go. It's too costly and too slow. Okay, in 2019, this is just 5 years ago, here's the state of affairs according to the American Society of Mechanical Engineers. This is in November 2019. The International Atomic Energy Agency, looking ahead to 2050, sees the most optimistic global electricity market share for nuclear as only about 5%, down from the 10% today. And in the United States and Europe, it steadily declines to between 3 and 5% of the market, constituting a potential for market failure. In other words, nuclear might simply price itself out of the market altogether. This was also reflected in the bubble. You might remember the boom in uranium prices back around 2008. This is, by the way, before the 2011 triple meltdown in Fukushima. The price of uranium soared to a very high degree based on speculation about this nuclear renaissance, which in fact never really happened. And consequently, the price immediately dropped back down again and dropped even further down after the 2011 triple meltdown in Fukushima. So it was all based upon a bubble, a speculative bubble that never materialized. So let's take a look at the competition. The competition in terms of non-carbon emitting energy is, of course, renewables. Renewable energy is, of course, primarily hydro as a solid baseload electricity, and then, of course, the more intermittent wind and solar. Well, if you compare the key expansion periods of innovative technologies using this same period, 2010 to 2020, this is the same period where the nuclear renaissance was supposed to be occurring. And you will notice that the annual deployment growth of batteries, solar modules, wind, onshore and offshore wind was very high. They were increasing on the average 24%, 13%, 19%. In the case of storage, 69% per year. And at the same time that it was growing in capacity, these same technologies were dropping in price like a rock. For example, solar PV modules, that's solar photovoltaics, were dropping by about 18% per year in terms of price. So the price was dropping like a stone, and it made it much more affordable. And very quickly, it outpaced nuclear, which was getting more and more expensive as time went on. The renewables were getting cheaper and cheaper and more abundant. If we look at the same period, 2010 to 2020, this is from the US Energy Information Administration. You will see from the graph there on the left that the green line, which is the steepest line, is renewables. And the red line at the bottom is nuclear, which is not increasing very much at all. From 2010 to 2020, nuclear is pretty well flat, whereas the renewables are soaring very fast. And if you project that, if you extrapolate that into the future, you see that it outpaces everything else in terms of energy supply. So the graph on the right, the bar graph on the right, shows that even the bottom level, which is the nuclear, even while it's increasing in quantity, it's decreasing in market share. So it's going down, for example, here from 5% to 4%. So that's basically the problem that nuclear has. It's got much cheaper alternatives, the competitors that it's combating with for the market share. If we turn to Wall Street, the most impressive company is Lazard, who predicts levelized cost of energy comparisons for their investors. And if you take a look at the three red bars that I've colored them red, they weren't red in the original, solar plus storage, wind plus storage, you'll notice that even the largest estimated cost of solar and wind is far less than the lowest cost of nuclear. So nuclear is fighting an uphill battle because wind and solar at the lowest levels is more than 3 times cheaper than nuclear. So you can build 3 times as much, and it's much faster to deploy. So it means that you can build it faster, and you can also spend less money, and therefore have more money left to build more. So it sounds pretty obvious that nuclear is not the best investment if you want to get quick results. Obviously, the fastest and cheapest option is renewables. And that's strange that Canada and the Canadian provinces seem to be placing an emphasis on nuclear, which is the most expensive and the slowest and the most speculative, because the nuclear projects that are being proposed have never been built before and they've never been tested before. Whereas the wind and solar, they have been tested, they work fine. So at COP28 last year, there was an official position that was adopted by almost 200 nations to triple renewable energy and double energy efficiency by 2030, which is seen as a difficult but possible feasible job. Meanwhile, using the COP28 as a backdrop, but not being officially presented as a policy, there was a group of 25 nations that's recommended tripling nuclear power by 2050. Notice, please, that that's 20 years later than the target for tripling renewables. So 20 years later, you triple nuclear power, maybe. Most people, however, are thinking that that is far too much money. In fact, in Belgium, when they had a nuclear summit discussing this very issue within that same calendar year, the bankers who attended that meeting said there's no way that the banks would finance this. They would not put up the trillions of dollars necessary to triple nuclear power by 2050. So it would have to be depending on government money. Now, here is a COP28 goal of tripling global renewable capacity by 2030, showing what happens up to 2024. And already the renewables are doing very well. If you just extend that trend, you can see that it is perhaps feasible to achieve the tripling by 2030. Right now, the blue dot there represents the current ambition, the current estimate of 79,000 gigawatts. We're hoping that we can step it up and increase the installation of renewables by more than that to get that tripling. Now, the International Energy Agency has predicted that in the next 10 years, 90% of all new electricity production facilities worldwide will be renewable. So now, just as an indication, oftentimes people are concerned about the actual capacity of renewables to meet electricity needs. So I'm putting this in here. It's a little bit out of context, but the current electrical capacity in Michigan is a bit more than 30,500 megawatts. The potential for offshore wind in Michigan, according to studies that were carried out by the well, the article is represented there. Offshore wind in Michigan, great potential, many challenges. The potential for offshore wind in Michigan is over 320,000 megawatts. That's more than 10 times the amount of capacity that is feasible. Now, that's more than 10 times the current capacity, and it's about 1/4 of total US electrical capacity. So there are great potentials if you take a look at what is possible to be done. Obviously, there are many practical obstacles that would interfere with that, navigation being one of them. So let's now take a look at what the problem is with nuclear power. Why is nuclear power not able to compete better with the renewables? Why can't they strip down and produce cheaper cost savings and strip down the time? So let's take a look at the nature of the beast. In 1943, Canada's first early involvement with nuclear came as a result of World War II plans. In 1943, our Prime Minister, who was Mackenzie King, met with Roosevelt and Churchill, and they signed an agreement to cooperate in building the world's first atomic bombs. Now, the reason why Canada was involved in that is because Canada was the main supplier of uranium. In North America, the only really readily available source of uranium was in Canada as a result of an earlier radium mine that operated in the Northwest Territories. Way up north on this map in Great Bear Lake, there was a radioactive ore deposit discovered in 1930 at a place now called Port Radium. And at that time, radium was a very it was selling for about $70,000 a gram at that time. No, I think it had already dropped to about $40,000 a gram. And what happens with uranium is that it's a byproduct of uranium. And so when there's radium, there's bound to be uranium. And it was the uranium leftovers that played a key role in the bomb project. Now, here is the result in Hiroshima of one single uranium bomb dropped on a city from an airplane. One single uranium bomb, and look at the devastation it causes. So it makes you wonder where, and me certainly as a scientist, I was curious, where does all this energy come from? How could it be possible that uranium has so much energy? This was first indicated way back in 1896 when Henri Becquerel in Paris discovered radioactivity of uranium ore. He discovered that if you took a rock containing uranium and it would be able to give off a kind of an invisible radiation that would develop a photograph, would cause shadows on a photographic plate, even though the photographic plate was wrapped in thick black paper. So you can't see radioactivity, but if you put a piece of uranium ore into a device called a cloud chamber, you can see the tracks of the energy that's being given off, the particles that are emitted from the rock. And it's amazing that this amount of energy is being given off 7 days a week, 24 hours a day for millions and millions and millions of years. And it makes you wonder, where does all this energy come from? In fact, if you do a mathematical calculation and add up all the energy over a few thousand years, you discover that it would be enough to destroy large parts of the Earth. But in the early days, they didn't see any way of getting that much energy released all at once because there was no trigger. Radioactivity cannot be speeded up or slowed down or stopped by any method known to science. And that's why we have a radioactive waste problem. Now, a couple of years later, Marie Curie, who was a brilliant chemist, she crushed up the uranium rock that Becquerel was looking at, and she discovered that when you extract the uranium chemically, you discover that it is radioactive indeed, but the leftovers, the crushed rock, is actually much more radioactive than the uranium itself. 85% of the radioactivity is in the crushed rock. And she discovered two elements called radium and polonium that are actually byproducts of uranium. By the 1920s, it was realized that handling uranium is deadly dangerous. These young teenage girls, thousands of them, were used to paint dials with radium paint to make them glow in the dark without any external source of energy. And they developed horrible deaths from fatal anemia, from bone cancer, and from head cancers later on. First, it was demonstrated that they had something called radium jaw, where their teeth were falling out. And when the dentist tried to repair the teeth damage, the jaw bones would break at the slightest provocation. So the jaws were being, the bones of the body, in fact, were being weakened. Later, there were fatal anemias and then bone cancers, an epidemic of bone cancers and head cancers. By the end of the 1950s, by the beginning of World War II, it was realized that radium was far too dangerous for any commercial use. Meanwhile, underground miners developed lung cancer. The people who were mining the radium ore in Navajo country, and that was due to radon gas. And that was found out way back in 1930. They knew that it's the leading cause of lung cancer among non-smokers. Now we know that. And it was determined that it caused lung cancer in underground miners. For hundreds of years, this had been happening in Czechoslovakia without people knowing what the cause was. Although radon is a gas, and if you breathe it in, you will breathe it out just as easily, it actually turns into solids. When the radon atoms disintegrate, they turn into polonium atoms. And polonium is extremely dangerous. And that's most of the damage to the lungs is done by the polonium that's deposited there. Now, this is a man, Alexander Litvinenko, who in 2006 was murdered in London, England, using a small amount of polonium-210. He was it appears that Vladimir Putin sent murderers to kill him because he was critical of the regime. And he died a terrible death as a result of polonium that was put into his tea. It was at that point I investigated and I found out that polonium, according to the American Health Physics Society, it's probably the cause of up to 90% of the deaths that are attributed to tobacco, because tobacco plants, when they grow, they use radioactive fertilizer on the crops, and radon gas produces polonium that is absorbed into the tobacco leaves and harvested and ends up in the cigarettes. Meanwhile, the Los Alamos Nuclear Laboratory down in Los Alamos, New Mexico, pointed out that weight by weight, polonium-210 is 250 billion times more toxic as hydrogen cyanide, which is one of the fastest acting deadly poisons that we know chemically. So the main point here is that tiny, tiny amounts of radioactive materials can be extremely dangerous. Now, the radioactive disintegration that occurs, we now know, consists of giving off particles and rays, gamma rays, alpha and beta particles, which do a lot of damage to living tissue, and in particular by damaging DNA molecules, causing biological organs to grow improperly, to grow abnormally, and leading to cancer and a number of other problems that can be very serious, including genetic disabilities that can be passed on to future generations. Now, some of this radiation is not very penetrating, much to some people's surprise. For example, alpha radiation cannot penetrate through a piece of paper, and yet it's hundreds to thousands of times more dangerous than gamma radiation once it's inside the body. So if you have an alpha emitter that gets inside the body, it can do an awful lot of damage, especially since it lodges there and gives radiation over a long period of time. It radiates the tissues. Here is a picture taken by my friend Robert Del Tredici through a microscope of a small particle of alpha-emitting material. It's actually plutonium in the lung tissue of an ape, and you can see those spikes are actually the tracks of alpha particles given off over a 48-hour period from that tiny speck of plutonium dust. And you notice the radiation doesn't go very far. But what it does is it damages the cells in the immediate vicinity, and those cells can many years later, up to 20 or 30 or 40 years later, develop into fatal lung cancers. And these lung cancers have a very high mortality, well over 95%. So they knew this way back in 1931. As early as 1931, there were documents produced by the Canadian Department of Mines stating that the lung cancer, bone necrosis, and rapid anemia are possible diseases due to the deposition of radioactive substances in the cell tissue or bone structures of the body. This warning was for the scientists in Ottawa who had to handle small amounts, not the ore carriers or miners in the Northwest Territories who actually faced large exposures from this material. And as a result, the village up in the Northwest Territories called Delaney is now sometimes called the Village of Widows, because so many of the men have died as a result of exposure to this radioactive material. Now, when we mine uranium in Saskatchewan or elsewhere, we leave behind the crushed rock, which Marie Curie looked at. These are the radioactive uranium tailings, and they contain all the polonium, all the radium, and all the radon gas that was in the ore originally. And the effective half-life of this material is 76,000 years. It'll take 76,000 years for the amount of each one of those materials to diminish by a factor of a half. This 30-foot wall that we show here is in the Elliott Lake area of Ontario. It holds back a lake of 70 million tons of radioactive sand from uranium mining. A permanent legacy. Radioactivity is a form of nuclear energy that cannot be shut off, and that's why we have a nuclear waste problem. So everything changed in 1938. Christmas 1938, all of a sudden they discovered that trigger that was not known before. That trigger is called a neutron. A neutron can actually act as a trigger to release an awful lot of this nuclear energy all at once by starting what's called a nuclear chain reaction. When a neutron hits an atom of uranium-235, a rare form of uranium, it can split the nucleus, and you get two smaller atoms given off, which are called fission products, along with 2 or 3 extra neutrons. Those extra neutrons, they trigger more fissions, and some go on to produce even more radioactive waste than the fission products. So this is where the radioactive waste comes from in a nuclear reactor or in a nuclear bomb, and this is where the energy comes from as well. Now, this is a statue that Bob photographed in the ex-Soviet Union. It's a statue to the splitting of the uranium atom. And the two hemispheres represent the broken pieces of the uranium atom. The semicircles represent the energy that's given off. And the man in front is a statue to the man called Kurchatov, who was the father of the Soviet atomic bomb. Here is a picture of an American scientist standing in front of some photographs of atmospheric explosions. You know, they tested these things in the atmosphere for many years down in the Southwest United States and in the South Pacific. And that's one way that the fission products can become disseminated as radioactive fallout. And in fact, that radioactive fallout is still coming down even today from the stratosphere. So in Canada, although we contributed to the atomic bomb project by selling uranium to the American military, we decided to go for the peaceful uses of nuclear energy. And we built CANDU fuel bundles and CANDU reactors that could harness this energy hopefully for good, so that we could produce abundant energy without emitting carbon dioxide, although that was not a major consideration originally. Now that's certainly an advantage. And the sheer density of energy, this ad is called Small Wonder. The man who is an actor is holding a simulated uranium fuel pellet, and he's saying that isn't it amazing that this fuel pellet contains as much useful energy as a carload of coal. And therefore, it's very, very condensed energy, very concentrated. And that's one of the main advantages, along with the fact that it doesn't depend upon combustion and therefore does not produce carbon dioxide. This is the face of a CANDU reactor. One of the things I should have said, however, is that if these fuel bundles had ever been used in a nuclear reactor, this man would be dead. Because after they come out of the reactor, although the fuel bundles can be handled safely when they're only uranium, when they come out of the reactor, they are millions of times more radioactive than when they went in, and they will kill any human being in less than 20 seconds at a distance of 1 meter. So these things can never be handled again by human hands. They have to only be handled robotically. Here's a man standing in front of the face of a CANDU reactor at Darlington. This was before the reactor ever operated, and as a result, he can stand there safely. If the reactor had ever operated, he would be putting his life in jeopardy by simply standing there. He'd be dead rather quickly as a result of massive blast of gamma radiation. The fuel radiation, when these fuels are when the atoms are disintegrating, they're giving off energy, and all energy converts eventually to heat. And so the heat from the disintegrating atoms in a nuclear reactor are sufficient to melt the core of the reactor, even after the reactor shut down. So if you shut down a reactor immediately, you still have about 7% of full power heat being generated by the radioactivity alone. And that's enough to melt the core of the reactors. That's what happened at Fukushima back in 2011. Those reactors were safely shut off before they started melting down. In Canada, we have a spent fuel pool about 40 feet deep, in which the fuel has to be stored. The used fuel has to be stored for about 10 years in circulating water in order to keep the fuel from overheating spontaneously, which it will do if it didn't have that cooling water there. Now here's a hydrogen gas explosion of one of the Fukushima reactors. When the fuel overheats, if you can't remove the decay, so-called decay heat caused by radioactivity, then you get the generation of hydrogen gas chemically as a result of a chemical reaction. And that is very explosive. And so the hydrogen gas can ignite and explode, which almost always happens when there's when there's a nuclear meltdown. There's almost always hydrogen gas explosions that ensue. And this is one example of one. Here is the result of that kind of an explosion in Fukushima. The reactor is really destroyed, not by the tsunami, not by the earthquake, but by the internal forces of the uranium fuel in the reactor. It's just the heat generated by the reactor and the chemical reactions induced by that heat that caused this destruction. Here we have a scattering of radioactive materials over a huge area, about 250 miles radius. And they had to collect garbage bags full of radioactive soil and radioactive rocks and radioactive debris, even from the forest areas. They cleaned out the bottom of the forest within 20 meters of human habitation. But if you go outside that 20-meter radius, the radiation levels to this day are still very high. So this graph shows the radiotoxicity of 1 year's worth of spent CANDU fuel from one reactor over a period of 10 million years. So this hazard lasts for a very long time. And that's one of the real downsides of nuclear power, because every reactor, it doesn't matter how small it is, it doesn't matter how big it is, every reactor produces these high-level radioactive waste, the fission products, the actinides, the activation products, which are the result of nuclear fission. And they become a permanent radioactive legacy for the human race. We don't know how to turn it off. Dave Geary of Saskatoon made this wonderful graphic just showing how radioactive materials are materials after all, and they do have chemical properties. And depending on their chemical properties, they go into the food chain, they go into the water, they go into the air, and they go into the human body, and they follow the same pathways that non-radioactive materials would follow, because most of these materials are not radioactive in nature. For example, radionuclides are chemical substances that are also radioactive, and they go to different organs depending on the chemistry. For instance, iodine-129 or iodine-131 are radioactive versions of otherwise non-radioactive iodine. Iodine in nature is not radioactive, but these ones are. So nuclear power creates, you might call radioactive twins of non-radioactive materials. It goes to the thyroid gland and it damages it and causes thyroid cancer and other disorders. Cesium is another example. It goes to the soft tissues of the body, it goes to the blood and the soft organs, and therefore it contaminates meat, makes them unfit for food. For example, sheep farmers in northern England and Wales could not sell their sheep meat for 20 years after the Chernobyl accident because of radioactive iodine contamination of the meat. Even today, hunters in Germany, Austria, and the Czech Republic, if they hunt boars and kill a boar, they can't eat the meat because it's too radioactive. The boars are very good at accumulating this radioactive cesium into their tissues. Here in North America, the caribou received more radioactive fallout than any other animal, basically, from the Chernobyl accident. And the longevity of these wastes. The bulk of the future radiation dose comes from long-lived fission products like selenium-79. Notice selenium-79 has a 327,000-year half-life. Technetium-99, a 210,000-year half-life. Cesium-135 is a 2.3 million-year half-life. Iodine-129 is almost a 16 million-year half-life. So that's why these wastes remain dangerous for a very, very long time. It's not a question of just waiting for a few decades. No, you really have to wait forever, and you really have to keep it out of the environment of living things forever if you want to have a hygienic environment. As I mentioned earlier, the lethality of a freshly removed fuel bundle is such that a person standing within a meter of it would die within an hour. He'd get a lethal dose in 20 seconds, but it'd take him an hour to die. Now, a fuel bundle looks solid, but radioactive materials do leak out through tiny pinholes and cracks. Severe fuel damage causes massive leaks. And of course, if you have a meltdown, then you get a huge release of radioactive materials. As the fuel pellets, I showed you one of those fuel pellets earlier, they look very solid. They're solid ceramic materials originally, but in the reactor, when they're being used, they crack and they fissure, they become fractured. And a lot of the radioactive materials end up in the gap between the pellet and the cladding, the coating outside it. And so therefore it can be released immediately as a kind of a gas. This is true of radioactive iodine and radioactive cesium in particular. When a CANDU reactor is operating, all the radioactivity, all the new radioactive materials are created in the core, the reactor core where the fuel is. But because the fuel bundles do leak, some of that radioactivity goes throughout the primary heating system, and the steam generator ends up being the central part of it. ends up being quite radioactive, highly radioactive, because of the accumulation of material that's leaked out of those fuel bundles. So let's just take a look at what happens after it comes out of the storage pool. It goes into what's called a dry storage cask. Here's a cutaway section of a dry storage cask. Empty, it weighs 60 tons. Full, it weighs 70 tons. So there's only 10 tons of radioactive fuel in there and a 60-ton container to provide protection. You see how massive it has to be. This is one of the reasons why it's difficult for reactors to be small. In order to make them small, you have to reduce the shielding. And if you reduce the shielding, then you endanger the workers or possibly the public. And you also provide less of a barrier between the radioactive waste and the environment outside. You'll notice at the very top, there's a little red thing called a safeguard seal. That safeguard seal is for international inspectors to verify that nobody has gone into that container and taken out the plutonium. There's enough plutonium, about 40 kilograms of plutonium, which is enough for 6 or 7 atomic bombs inside that dry storage container, because every nuclear reactor simultaneously produces plutonium as a byproduct, which is heavier than uranium. It's not a fission product, but it is a result of nuclear fission. What happens is that there's an element there's a type of uranium called uranium-238, and when it gets struck by a neutron, instead of splitting, it turns into a new material called plutonium-239. And that plutonium-239 is the raw material for most of the atomic bombs and nuclear weapons in the world today. In fact, it's not available in nature. You can't find a plutonium mine except in places where we've created a plutonium mine. When we sell reactors overseas, we're creating a plutonium mine because the spent fuel is the plutonium. That's the container of the plutonium. Anybody, many thousands of years into the future, can go to that waste and extract the plutonium from it and use it to make atomic bombs. This glass paperweight is the exact size of the plutonium ball that was used as a nuclear explosive in the Nagasaki bomb. So that's really one of the major considerations. By the way, plutonium is also required for even the large H bombs, the much more powerful H bombs. They have to have plutonium as a trigger to get them started. You detonate the plutonium, it's a small plutonium atomic bomb, just to raise the temperature to 100 million degrees Celsius, which ignites the fusion weapon. And those fusion weapons can be 1,000 times more powerful than the Hiroshima bomb. The Hiroshima bomb, in fact, is now considered to be a very small bomb, and they don't make them that small anymore for the most part. Most of them are, even the ones that go in the head of a cruise missile, are about as much as 15 times more powerful than the Hiroshima bomb. So that's one of the major concerns people have about uranium is the connection with nuclear weapons. Now, in order to make the Hiroshima bomb, they had to increase the concentration of U-235, which is only 0.7%. That means 7 atoms out of 1,000. That's the red. 7 atoms out of 1,000 are uranium-235. That's not enough to make an explosive. You've got to increase that percentage up to as high as possible. If you get it up to about 90%, then you have what's called weapons-grade uranium. That's what the plutonium, that's what the uranium in the Hiroshima bomb was made from. Now, here in Saskatchewan, they're talking about building an E Vinci reactor, a small nuclear reactor that only generates about maybe 5 megawatts of electricity, only about 15 megawatts of heat. It's very small, but the fuel that they're going to use in that reactor is highly enriched, almost highly enriched. It's 19.75%. If it gets to 20%, it's called highly enriched, and everybody agrees that highly enriched uranium is a danger for weapons users because they can make nuclear weapons from that. Well, guess what? They've now discovered that that 20% is not a firm cutoff point. 19.75% is almost certainly weapons usable. And there's articles now in Science magazine about the usability of highly enriched of uranium that's low enriched, but very close to being highly enriched, that they can be used in weapons also. So there's a very real concern here about proliferation when we use these kinds of reactors. But this is a picture of an overhead picture of an old-fashioned uranium enrichment plant in Portsmouth, Ohio. A great deal of the U-238 has to be removed in order to get the enrichment to take place and to make bombs. And the depleted uranium is left in the field. It's mostly U-238 that's left over, and that can be used by the military and is used by the military to make the plutonium for their nuclear weapons. It's used as what's called target material in special reactors called plutonium production reactors. So let's turn now to small modular nuclear reactors. The whole idea of the nuclear industry is that, look, we're not doing well. Our industry has been stagnant for 25 years. Our market share has gone down from 17% to 10%. Now it's about 9%. So we need to somehow break out of this doldrums. Let's try, since we can't sell the large reactors, let's try and sell small reactors. We'll call them small modular nuclear reactors. And that's what we're now, that's the flavor of the day for the nuclear field. And notice, by the way, they conveniently leave out the word nuclear in their acronym. They call them SMRs, whereas I insist upon calling them SMNRs, because it's actually the N that causes all the problems. All fission reactors create radioactive waste and nuclear weapons material, plutonium. Small modular nuclear reactors are not clean, not small, not green, not affordable, according to me and my organization. And part of the reason for that is they simply don't mention those things that make nuclear power uniquely undesirable. They don't talk about the radioactive waste. They don't talk about the reactor accidents that can occur. And they don't talk about the nuclear weapons proliferation aspects of all these reactors. This is a resolution from the Chiefs of Ontario back in 2018 against small modular reactors, asking Canada not to go down this path because it's a dangerous path to go down. And of course, it turns out that Indigenous communities are often the ones who are most directly affected by the negative effects of the so-called nuclear fuel chain, both at the beginning with the uranium mining and at the end with the nuclear waste disposal. It's largely Indigenous communities or lands adjacent to Indigenous communities that are affected. Now, let's take a look at one of the small modular reactors that we're talking about. This is one that's proposed to be built in Ontario, in Darlington, on the Darlington site, just east of Oshawa, on Lake Ontario. And Saskatchewan has indicated that it would like to maybe buy one of these if it works out well in Ontario. Now, they call it a small modular reactor, but you know what? This plant goes 10 meters high above ground and 11 meters below ground, 11 stories below ground. So 10 stories above ground, 11 stories below ground. That's a total of 21 stories, a 21-story building. Who would call that structure small? This is not a small reactor. It's also not modular because you have to have a workforce of about 1,000 people to dig the hole and build this whole structure underground. The core of the reactor, where all the radioactivity is, and all of the control mechanisms are underground, and they are also surrounded by water because this whole excavated cylindrical hole will be filled with groundwater, and it's only about a couple hundred meters from the shore of Lake Ontario. So it's a very unusual design, and it seems to be designed to try and minimize how big it really is. Now, if we take a look at this thing, it's called the BWRX 300. There's a diagram there in the middle, which corresponds to a diagram on the left-hand side, which is a precursor of the BWRX 300. It's called the Economic Simplified Boiling Water Reactor. By the way, the Economic Simplified Boiling Water Reactor is a modification, a simplification of the first Fukushima reactor that melted down. Fukushima Unit 1 that melted down, that was a boiling water reactor, and it was a precursor of the economic one, the ESBWR. Now you notice that there's about a 90% reduction in size to go to the BWRX 300. So how do they manage to make it so much smaller? Well, one thing they do is they eliminate a lot of the safety systems. Safety systems take up a lot of time. And also if you have pools of water, suppression pool, you notice on the left, there's several pools of water there. most of those pools of water have been eliminated, and they only have one pool of water left, and that's the pool of water at the top there, which is called an isolation condenser system. And that's supposed to handle all the nuclear accidents that that nuclear reactor might encounter. If there's a loss of coolant or if there's any kind of overpressure, that small tank of water is supposed to do the job in all those eventualities. Now, the U.S. Nuclear Regulatory Commission has not yet licensed this, the smaller one, because they still have questions about the safety of it. But right now, there are hearings underway in Ontario to license the building of this reactor, even though the design is incomplete and many of the safety questions have remained unanswered. Here in Saskatchewan, you're also talking about a new reactor I mentioned earlier, the eVinci reactor. You may know that the Saskatchewan Research Council, has been given $80 million by the province to investigate this particular design. And they want to build a model somewhere in Saskatchewan, maybe in the Elbow region, maybe in the Estevan region, in order to see how it works. And this is the reactor that I mentioned before, has 19.75% enriched uranium. Now, when you enrich the uranium, that means you also enrich the fission products by the same amount. So this particular fuel is about 28 times more concentrated in U-235 than ordinary CANDU fuel, Canadian CANDU reactor fuel. And that means the fission products are also about 28 times more intense in the used fuel. So in fact, the radioactive inventory in this very small reactor, 15 megawatts of heat, would be equivalent to a CANDU reactor generating 420 megawatts of heat. So even though it's a small reactor, it has a hell of a lot of radioactivity in it, far more radioactivity by a factor of about 30 than any CANDU reactor today existing. They say that they're going to put this reactor in place and then take it away again after it's finished. Well, I don't know exactly how they're going to shield the workers when they take it away, because it's going to be extremely radioactive, and because it's small, it doesn't have a whole lot of shielding to protect people. It also doesn't have much of a barrier to the environment in case there was something, well, for example, like a military attack. I mean, I know that that's not likely in Saskatchewan, but if they want to sell these reactors in other countries, it could easily happen. Look at what's happening in Ukraine right now. And this reactor has nowhere near the ability to withstand a military attack that those large reactors have that are now at Zaporizhia in Ukraine. So there's another factor that we have to be concerned about, and that is that more and more the nuclear industry in Canada is talking about recycling the fuel, the waste fuel. Now, when they talk about recycling it, what they really mean is to extract the plutonium and leave the rest of the crap behind. So what they really want to do is take the plutonium out and use the plutonium as fuel. It can not only be used as a weapons material, it can also be used to fuel a nuclear reactor. But in doing that, you have to destroy the fuel bundles. You have to release all the radioactive materials inside, and those things cannot be recycled. Those things end up being radioactive waste, which then have to be resolidified and stored for the next 10 million years. So I've given you an article there, Reprocessing Revisited, a 2008 article by two gentlemen who are very knowledgeable about this whole topic, Edwin Lyman and Frank von Hippel. So I recommend that article to you. Now, in 2023, just last year, the U.S. General Accounting Office, which is called, now it's called the U.S. Government Accounting Office, so I apologize for using the wrong name there. It's the Government Accounting Office now. It used to be called the General Accounting Office. It says that Hanford, this is out in Washington State, Hanford is one of the largest and most expensive environmental cleanup projects worldwide. We estimated in 2022 that the cleanup will cost between $300 billion and $640 billion. Imagine. Now that's from reprocessing. That's from, this was a military operation to extract plutonium for military use. However, civilian reprocessing would also be very damaging as well because of the extreme difficulty in containing all the radioactive materials that are in the spent fuel. Here we have several hundred tanks of high-level radioactive liquid waste, which remain dangerous for many millennia. Of course, when we sold a reactor, we gave a reactor, we didn't sell it to them, we gave it to them, a 40 megawatt heat generating reactor to, that's even more powerful, by the way, than the E. Vinci reactor in terms of heat. We gave that to India, and India used the plutonium from that reactor in the first atomic bomb in 1974. So the trouble is, spreading these reactor technologies around gives people the ability to make atomic bombs using the leftovers. Now, reprocessing, you see, the bomb is not so easy to get from a nuclear reactor for the simple reason that the radioactive waste is so damn radioactive that you can't come close to it. Anybody who tries to carry off a uranium fuel bundle, a used one, will probably die before he gets out the door. So, but what happens with reprocessing is you take away that firewall, that radioactive firewall, and you replace it with what's called a reprocessing plant. And once the reprocessing plant is built, you can take the plutonium out the front door and use it for fuel, but you can also just as easily take it out the back door and use it for bombs. So it's a proliferation machine for sure, in terms of all the countries in the world today, especially with the demonstration. You know, Ukraine had nuclear weapons and they gave them up. Look what happened to them in terms of the relationships with Russia. North Korea has nuclear weapons and it does not give them up. And as a result, there's a kind of a standoff with the United States and the superpowers because nobody knows exactly what to do about North Korea's nuclear weapons arsenal. Well, it's not very long in the future that every country in the world could have its own nuclear arsenal if we promulgate these nuclear technologies, which are so-called advanced technologies. These advanced technologies are more dangerous than the ones that we already have, far more dangerous in terms of the radioactive waste, which is far more radioactive per kilogram, in terms of the usable military materials, which are far more accessible than previously. So what we've done is we're in the process of converting the nuclear fuel chain, which goes from the mine to the mill, to the refinery, to the fuel fabrication, to the waste. We're turning that chain into a genuine cycle. And when we change it into a cycle, that means we have the enrichment capabilities and the reprocessing capabilities, that's the plutonium extraction, that they can lead directly to bombs if you have a regime which is determined to do that. And I again mention once again that this conversion to bombs can be made at any time in the future. So you can't just judge by the existing regimes. You have to think about what kind of regime change might occur in the future. Look at, for example, the transition from Biden to Trump. What a dramatic transition. Look at the transition from the Weimar Republic in Germany to Adolf Hitler just a few years later. So you can't really predict what a country is going to be like in the future. And by the way, the agreements that are in place to prevent this from happening, any country can back out of those agreements with 3 months' notice. That's what North Korea did. North Korea was a signatory of the Non-Proliferation Treaty, and they simply gave notice that they're dropping out, and 3 months later, they were free to do whatever they darn well pleased. So this is a picture that Robert took in Kazakhstan. These are Kazakh women who are finding out for the very first time that their river, the Techa River that flows by their village, was contaminated by high-level liquid radioactive waste from reprocessing from the Mayak reprocessing plant in the Soviet Union, and that's the reason why so many people have got sick and died over many, many years. They were told over the many years in between, they were told by doctors and scientists who were refused permission to use the word radioactivity or radiation. They were told that people were dying of vegetative syndrome, and it was simply a euphemism for radiation poisoning. And these girls were finding this out for the first time when Bob took this picture. And he sees this as emblematic of the fate of the human race itself. We're all in the position of these women. We have to look ahead if we want to know what's in store for us. And if we want to avoid what, we have to use our third eye and use forethought and foresight rather than waiting until it happens and living with the consequences. And for this reason, my organization, and for other reasons, my organization is against the current policy of the Canadian government and the Canadian provinces to focus on the most expensive and slowest, most dangerous, and most speculative energy source for the future. Thank you.